Hello, everyone. So the Federal Arctic Research Plan has an element which says it's for integrating Arctic observational and modeling data through data assimilation and reanalysis. To address this, the MOMP team and the modeling team began a meeting series with sea ice data assimilation last September. So this would be the second meeting in that series. So land ice data assimilation might be considered independently from assimilation methods used in sea ice or elsewhere in the Earth system for that matter. Ice sheet modeling and ice sheet data assimilation require unique considerations. Ice sheets may be thought of as very large integrated systems that respond to forcing on very long timescales, glacial timescales. Available observations on the state of ice sheets are also more limited. Nevertheless, there have been significant developments in data assimilation that are complementary to the development of ice sheet remote sensing and ice sheet models over the past decade or so. For Arctic ice sheets, we are, of course, talking about Greenland, although some discussion of Antarctica or perhaps mountain glaciers may also be relevant. So today we will hear two presentations on recent work in land ice data assimilation. Our first presenter is Jessica Badgley. Jessica is the James S. McDonald Foundation Postdoctoral Fellow at Dartmouth College. And the title of her presentation is Improving Models of the Northwestern Greenland Ice Sheet with transient calibration from decadal trends to seasonal cycles. Jessica, welcome.
Thanks for having me. All right, I'll start by sharing my screen here. All right, can you all see this?
Yes, very good.
Yes?
Yes.
Advancing is working, okay. So yeah, thanks for having me. As Richard said, I'm a Dartmouth a postdoc at Dartmouth College. And I've spent these last 2 years thinking about land ice data assimilation, especially for Greenland, so I wanted to share some of that work. And some of this is built off of actually what Youngman has done, and so we coordinated to make sure we didn't overlap too much. But I'll be talking about a particular data assimilation method that's termed transient calibration in ice sheet modeling. And I want to focus on kind of two aspects of it. One, kind of decadal timescale trends, and the second, if we have time for it, seasonal cycles. So our goal number one will be to think about how transient calibration and investigate how it impacts model initialization, and we're going to be focused on Northwestern Greenland. One of the motivations for this is really the ice sheet model intercomparison project version 6, ISMIP 6, which was a really is amazing collaborative effort to bring a lot of different ice sheet models together to simulate both historical and future changes, particularly thinking about mass loss, and it's been used to think about how Greenland might contribute to sea level rise in the coming century. But one thing that the next version, ISMIP 7, has been focused on is how well or not well these models have captured historical changes. And so a paper, Ashwaubenon et al. 2021, for Greenland showed that these models from ISMIP 6 tend to underestimate observed mass loss over our observational record. And so one of the things that's been really people are thinking a lot more about is how are we initializing these models, and how can we better capture these historic trends so we can have more confidence in future trends. And then the second thing, if we get to it, is also how we can use transient data assimilation, in this case transient calibration, to understand processes going on in the ice sheet that may be really difficult to observe or understand. One is seasonal ice dynamics, which are, from the literature we know, these seasonal dynamics are primarily driven by changes in the ice front position, so think calving and melting at the ice-ocean interface, but also changes in basal conditions. For example, how much the ice is sliding along the bedrock, how much is subglacial hydrology contributing to that one. And this in particular, it's very difficult or in many cases impossible to observe the ice bed interface. And so we have to do a lot of inferring or modeling of that interface. Okay, so we'll start with the first one and see how far we get in these 15 minutes. So first, I wanted to start with, I wasn't sure how many people would be ice sheet modelers here, so think about how when I go about setting up a model, both setting it up and initializing it and what things I might need to consider. So first is we need to set up the geometry. A lot of this can be taken from observations or observations integrated with models. So we set up the bed topography, the surface elevation of the ice, which also gives us together ice thickness, where the ocean is, whether any of this ice is floating or not. And then we set up some forcings, again, might be taken from observations or models or a combination of both. So the surface mass balance made up of accumulation rate and ablation rate. And then we might even include other things such as a geothermal heat flux if we have a thermal model or if we are thinking about basal melting. And then we can use our setup geometry to calculate the stress balance velocity. And so here is a vertical profile of horizontal velocity that maybe we get from our model. And we see from a surface velocity observation that our model matches pretty well. So that's great. But there might be other locations where our model shows a certain velocity profile and it doesn't necessarily match what we observe at the surface. And so for Greenland especially, and a lot of Greenland's fast-flowing outlet glaciers, we also have to consider that there's basal sliding going on. And this is, as I mentioned, at the interface between the ice and the bedrock and quite difficult to observe. And so this is where we get into calibrating the ice sheet model for parameters that we don't fully either understand or aren't able to measure or model very well. And so we might calibrate or invert for these unknown parameters such as basal friction, how slippery the bed is. So we might find that there's a stickier bed, kind of an interior and more slippery bed where these faster flowing glaciers are. But there's other unknown parameters we might need to calibrate for or assume something about, such as ice rheology. Where is it softer? Maybe it's softer in the basal ice or in last glacial maximum ice, and where is it stiffer? And these will all affect the ice flow and the model. So for this talk, I'm going to just be focusing on, I'm going to assume ice rheology and that we know it, which is, we can talk about whether that's a good assumption, and then focus on calibrating how slippery the bed is, or this basal friction. And so we'll initialize our model by inverting for basal friction. And Youngman will talk about a different method, but kind of in general, when I think about this, we have some model that is uncalibrated. It's just based on our initial setup. And if we run it forward in time, we can look at some variable from it, such as surface velocity. And then we have some parameter we might not trust that we've gotten fully right. And we might be able to adjust it within some constraints to be able to match some data that we have, such as surface velocity. And so with various different data assimilation methods, you can then adjust this unknown parameter and get a calibrated model that helps you match your data quite a bit better. And so this has long been used in ice sheet modeling, but one of the kind of issues we've run up against time and time again, and people are really have been working on in the I don't know, last 5-10 years, is how do we incorporate the enormous amounts of data that we have? We don't just have data from one point in time, we have a whole time series and of data that covers most of the ice sheet, especially from satellites. And so kind of one of the big goals is to integrate more data into these ice sheet and model initializations. And so one thing that we've already done is we've used data constrained forcings and geometry to really get as good of a model set up as we can. And then there's ensemble data assimilation methods, such as the Kalman filter, like Youngman will discuss. And then there are variational data assimilation methods, or also known as adjoint or control methods. And in the ice sheet modeling community, we use these two terms, the snapshot inversion, which uses data from one point in time, and transient calibration, which is now possible in several ice sheet models to assimilate a whole time series of observations using transient physics. And so what I showed you before is an example of the snapshot inversion. But one of the things we've learned about the snapshot inversion is that though we may be able to match the data, we can get it's an under-constrained problem, and so we can get calibrated models that have totally different trends. And neither of them may match the data that we didn't calibrate against. And so this is where transient calibration comes in. By assimilating more of the data, we can get a model that doesn't perfectly match necessarily any of the data, but it captures the trends much better. And so I don't want to get too much into the math, but just to get away from a schematic and something a little bit more concrete. What we're really doing here in transient calibration, or in this adjoint data assimilation method, is we're defining a cost function, which is our data model misfit, in this case with velocity. And we might also have a different sort of data model misfit, such as log velocity, if we want to capture the slower flowing regions better. And then we have a regularization term. So this incorporates a priori information or assumptions about how variable the field should be or what it should look like. And so you can set up this cost function for any number of variables. In this case, we're doing just one, the basal friction coefficient. And then we calculate the gradient of the cost function with respect to that variable and adjust it using gradient descent until we reach some convergence criteria. So this is actually how both snapshot inversion and transient calibration work. It's just that transient calibration has this time dependence. Okay, so now diving into what I've actually done. I use the ice sheet and sea level system model, or ISSM, and this is a fairly standard setup that I'll start with. If you're not an ice sheet modeler, don't worry too much about the details, but I just wanted to lay these out there. I'm simulating northwestern Greenland from 2007 to 2022, using the shallow shelf approximation for ice flow. I have an adaptive mesh so I can resolve faster flowing regions better. A monthly surface mass balance. I prescribe monthly ice front positions using the level set method. I have a sliding law. I use various different ones. And then we start with just the snapshot inversion to try to get at the basal friction coefficient. So if we then look at the results from this model, which is fairly standard, and we look at a time series from 2007 or to 2022 of velocity for these 2 points in Greenland. One is Sirmik-Kulahek, or on Jakobshavn Isbrae, and then the other is Sirmik, also known as Upernavik Istram. And the black points are observations from GRIMP measures, and the purple line is my model result, which is actually not too bad for these two locations, but there is a bit of a mean velocity offset, and we're also not capturing all seasonal variations. And then importantly, for thinking about calibrating trends in mass loss, we see that the model is losing mass too slowly compared to at least one observation-based reconstruction of mass loss from Minkoff et al. 2021. And we use the same surface mass balance as they do, so we know that this is due to our ice dynamics. And if we look, we generally know that it's likely due to these velocities that are too slow for most places. And so we are going to move from using the snapshot inversion with just data from one point in time at the start of our simulation to transient calibration, where we use a whole time series of observations for this region that cover it spatially. And just to reiterate, calibrating for the basal friction coefficient in the sliding law. And so when we do that, now orange is the transiently calibrated model simulation. We see that it's doing a much better fit to the mean velocity, although it's not matching everywhere perfectly, because there is that regularization and that kind of need to dig into that the prior information. But this is the data we simulated, so it's not too surprising that we match it much better. But then if we look at mass loss, we see that we're now within the observational uncertainty. Now, of course, I've used data over this full time period and to assimilate into the model, but Youngman has a great paper showing that even if you assimilate data for a short period of time, you still capture future forecast trends much better than with the snapshot inversion. Okay, I'm running up against time, but I want to quickly at least mention how I'm also trying to use transient calibration to understand seasonal timescale processes. And then if people have questions, we can talk more about the details later. So first, we know that some of the seasonal variations come from monthly changes in the monthly ice front, or that terminus position. And so just as before, I should prescribe those monthly ice front positions using observations, and we see that we're capturing some of the seasonality for some glaciers, but not for others. Okay, so that captures some, but we also know that another process that's important is what's going on at the bed, and so we can actually use transient calibration to infer seasonally evolving basal friction and start to learn about what might be happening at the bed. And so instead of calibrating our model for a parameter that is constant in time, with transient calibration and this time-dependent information, we can actually calibrate a parameter that changes through time and fit the data much better. Now, of course, you want to be careful about doing this, but I think we have a pretty good reason for thinking that the basal friction should vary on a seasonal timescale. And then also to keep things simple, for now I've just used the exact same seasonal cycle in the basal friction each year, so just trying to get a sense of the average seasonal conditions at the bed. And so we'll just be repeating the same cycle each year. And so when we do that, we see that now for the Pernific Istrum, where we weren't capturing any of the seasonal velocity variations before, we are now capturing at least the average variability quite well. All right, so just to finish up, one of the cool things about the model with being able to include the seasonally evolving bed conditions and the seasonally evolving ice front positions is that we can start to separate out the two. And so we may have an average seasonal signal that looks, I don't know, more or less similar for these two glaciers. But if we use the model to look at the contribution from ice fronts versus from basal conditions, we can see that actually a Pernific Istrum is much more driven by changes at the bed, whereas Sirmiculahek is much more driven by changes in the ice front position. Okay, I'm going to leave it at that, and this is just the conclusion slides. Oh, those are a little different, but those are the two goals, and happy to answer questions about what I did and more of the results.
Thanks very much, Jessica. That's a great introduction to this topic. So if you have questions, I think the standard thing that I do is if you can raise your hand. Where do you raise your hand in the chat? No, I think that's under the React button. There's probably a raise your hand. Yes. So raise your hand and then I can call on you to ask a question. So I'm at an atmospheric data assimilation center. Some of what you've presented is vaguely familiar to me. So one of the things we do here, of course, is we try to constrain the observations as best as possible. We try to make sure that they are high quality and things like that. Are there any things that you do to ensure that the data that you're using, the observations that you're using are of high quality or would necessarily be conducive to assimilation?
Yeah, that's a great question. And this is the area that I have a little bit less expertise in. So I turn to Michaela King, who has been and will be more of a collaborator on some of this, who has a lot of expertise in the GRIMP velocity products. And so I chatted with her about, yeah, kind of for what we were doing, what would be the best data to use. But even after that, I had noticed that especially with some of the seasonal calibrations that some of the optical based satellite products for velocity were giving very weird seasonal signals and had more outliers. And so thus, yeah, not allowing me to capture that seasonal signal very well with the data assimilation. And so I think that's something that I would like to look into more to make sure that the data I am using is kind of as high quality as possible. The other thing is that I've only used velocity observations right now, but we can assimilate other sorts of data which might give us different information, such as ice surface elevation, or Youngman has actually done really cool work assimilating ice front position to think about calving laws. And so there's a whole kind of wealth of data that I haven't drawn on yet. But yeah, Richard, I don't have like a specific answer unless we talk about a specific data set, but it's definitely a concern because any errors will make its way into your misfit cost function and affect the assimilation.
That's great. Um, I also think that you showed, seasonal data assimilation, which is very exciting. So in ISMIP 6, it was just annual input data and annual output values. And so here you're looking at the seasonal cycle. I guess you've answered part of this, but are there any other issues that might be associated with assimilation on the seasonal cycle? I guess data quality might vary throughout the year.
Mhm.
I'm trying to think of what would be affected. I
Yeah,
don't know if you
data.
have, yeah.
Oh, yeah, data quality might vary, but also, I mean, for any of this assimilation, you have to think about what else is missing from the model. So if there's another major process that is missing, so say we didn't do monthly ice front positions, or there's a lot of error in those, um, then any of that error uncertainty could get just pushed into the basal friction coefficient, and we might be misattributing it. So if there's another seasonal process that we think is really important that we're not capturing in the model, then we might be misconstruing it as changes at the bed when it's really not. And so that's one thing that you have to be really careful about, I think, with all data assimilation, but especially as you allow it to change in time, thinking about what processes we're missing or might have the most error in the model already.
Okay, great. Any other questions for Jessica? Yes, Matt Hoffman.
Hey, it was neat to see the transient optimization where you're resolving the seasonal cycle of velocities. Can you comment on how that differs from if you were to do a snapshot inversion at each point in time, um, and what you've thought about how you would do projections from such an initialization where your basal friction field is obviously changing in time based on observation. So what do you do going forward out of the observation time period?
Yeah, those are two really good questions. So, one potential issue with doing a bunch of snapshot inversions at different points in time and using those instead of a transient calibration is that um, you need to be, I think, really careful to allow the geometry to also change, or else you're just changing your data set that you're assimilating, and any changes in the stress uh, that you're not capturing with a geometry change will get transferred to the bed. So again, just thinking about where are your errors, and what are you, if you do change that geometry to capture that the geometric changes seasonally, then perhaps a snapshot inversion could reproduce what we're doing with transient calibration. But the transient calibration is nice because it incorporates all of those physics already and all of those seasonal changes. And then to your second question, that's definitely something that I'm planning to think more about. The simplest thing to do is just assume that the seasonal cycle doesn't change, which is not a good assumption. We know it's not true, but it's one starting place to see how it might impact projections and whether we should be trying to include it or not. And if we think we should include it, then hopefully what I'm doing here can help us think about a parameterization that's not as expensive as a subglacial hydrology model, but also maybe a little bit more based on what we think is going on kind of physically. So use this simulation that I have that includes the seasonality to derive a parameterization that we might be able to use in the future as the geometry changes and as environmental conditions change. So that's one thing I would like to look into for sure.
Sounds good. Thanks.
Thanks, Matt. So one of the things that you get out of data assimilation is a whole lot of statistics about, how your data assimilation has changed a free running model. So the various things like that, which can maybe be used to improve your model or things like that. Do you have you looked closely at what these statistics are telling you about the ice sheet model, and does that give you any useful information?
I'm trying to think about what statistics exactly you're talking about. I know with like the ensemble methods, we get out a lot of statistics about uncertainty. Is that?
I think that's what I mean, yes.
Yeah, so one of the things about this particular method is that it's deterministic. And so you don't, with it, you don't necessarily get an estimate of uncertainty. There are some new studies showing there are ways to estimate the uncertainty from this method. I haven't implemented them yet. So I think that's one shortfall of this method, is that it is deterministic and it's giving you, for this model, for your data assimilation setup, kind of one answer, but not the uncertainty around that. And so that's one of the benefits of using an ensemble method, or but also there are now studies showing that we can get at uncertainty from this method. I just haven't done it yet.
Okay.
So,
Thanks very much,
I think
Jessica.
that would be important.
Okay. Thanks very much. All right, let's go on to our next speaker then. Our next speaker is Youngmin Choi. He is a visiting assistant research scientist with the Earth System Science Interdisciplinary Center at the University of Maryland at College Park. And the title of his talk is Data Assimilation for Ice Sheet Modeling Using an Ensemble Kalman Filter. And you're, okay, there you go.
Yeah. Okay, thank you. Thank you for having me today. And thank you, Jessica, for a great talk. I think that's a great introduction for our topic today. So I'm going to shift our focus slightly to using ensemble Kalman filter for data assimilation in ice sheet modeling. So, oops. Okay. So this is kind of remind slide for data assimilation in ice sheet modeling. So data assimilation for ice sheet modeling generally refers to kind of model initialization through inverse method as introduced. So there are two common methods. One is snapshot inversion, which use a single surface observation, for example, surface velocity, to infer unknown model parameters, for example, like vessel friction. And then This is a great method to produce the current state of the ice sheet, but it can introduce some artificial model drift from the initial state for the transient simulations. So transient inversion, which simulates longer time series of observation, could reduce those model drifts by reproducing the current trends of changes in glacial behavior. But this method requires some significant computational resources. For example, we need huge memory to store some information for calculating the gradients of the cost function. So this might be a problem if we want to assimilate very long time series of large data sets. So thanks to many satellite platforms these days, we now have access to a significant amount of data. So ISET2 data is one of the example of that large data set. So ISET2 data provides ice surface elevation measurements, which is spatially and temporally very dense measurement. So from about 2008 and 2009, now we have 5 or 6 years of data with 91 days of temporal resolution and just a few kilometers of cross-track spacing, which makes the data very dense and very variable. So it's also a similar situation for the surface velocity data. So again, thanks to many satellite platforms, but now we have velocity data every month or even a few days for temporal resolution. So, so to assimilate those large data sets, we can rely on the ensemble Kalman filter, which allows us to sequentially assimilate time series of data into our model. So to briefly show how this ensemble Kalman filter works in this figure, so the model state and uncertainty are represented by this green circle and this oval shape, and they are propagated forward until a point where observations are available, which are represented by these blue stars here. And then the model state is then updated to get closer to the observation, creating a new model state, which is represented by the red square here. So this approach has been used for many climate models like atmosphere and ocean models for decades, but it's less commonly used in ice sheet modeling compared to variational methods. Some previous studies for ice sheet modeling show some promising results for estimating the states and basal conditions of the ice sheet using a ensemble Kalman filter. So on the left figure here, they show that ensemble Kalman filter approach could reproduce the true bed topography, which is in blue here, from the random initial bed, which is in this green here. So on the right, this study shows that ensemble Kalman filter also reproduce the changes in glacial behavior related to ice dynamics. So the pink color here in this figure is the reference grounding line positions along the flow line, and the gray color is the estimated grounding line position from each ensemble member, and the mean estimated grounding line positions are shown in these black lines. So from figure B to D, they assimilate more observations, and as more data is assimilated, the estimated grounding line positions get closer to the reference grounding line positions. So both studies show very promising results of ensemble data assimilation for ice sheet modeling, but one of the limitations for those studies is that they use a flow line model, which means that they assume that ice flows in a only single direction along the flow line. So they have X and Y coordinates, but no Y axis, which may miss the some representation of the stress field components that can impact ice dynamics. So it's not quite appropriate for large scale ice sheet models. but they still provide a great insight for the application of this ensemble gamma filter to ice modeling. So we built our study based on these two studies. So we set up idealized ice model domain with the plan view model, which is more appropriate for large-scale ice model. And so in this figure A, ice is flowing from 0 to 600 kilometer this direction, and we have this downsloping bed topography between 300 and 400 kilometer in the x-axis, and floating ice here where x is larger than 450 kilometer. And then based on this steady state, we run the model forward for next 200 years to make this glacier retreat further upstream, losing ice volume. So we refer this model to the reference simulation for our experiment. So based on that model domain, we organized the twin experiment here, in which we can test whether ensemble gamma filter method can recover the true friction coefficient and true bed at the same time. So the upper figures are the true friction coefficient and bed topography fields, and then the lower figures are initial ensemble mean of friction and bed topography fields. So for the friction coefficient, we create a random field using a covariance model for the spatial dependency, and assuming that we know the mean value of the true friction coefficient. And then for bed topography, we assume that we have radar measurement of the bed topography along these tracks, which is shown in yellow here, which is perpendicular to ice flow every 30 kilometers. So we generate the kind of conditional random field of the bed topography, prescribe these measurements, and covariance model also. So as you can see here, we have like better match. We have measurement here, but we have some interpolation error between these measurements. So we create the 50 different friction coefficient fields and bed topography fields to generate initial ensemble simulations. So for the forward model, we use the ice sheet and sea level system model developed by JPL, and for the data simulation process, we use the data simulation research bed DART developed by NCAR. So this is the twin experiment. So the observations are extracted from the reference run. So observations we are trying to estimate here are surface velocity and surface elevations, assuming that they are observed at annual resolution for 30 years, which means that like every year for 30 years. And then we also assume that they are observed at every ISM mesh node, which means that the full spatial coverage of the model domain. So these are the results. The red figure shows the true friction coefficient on the top, and the mean of initial ensembles on the second panel. And the third panel is the results, the friction coefficient after 5 years of data simulation, and then D is 15 years, and the last one is the after 30 years of data simulation. And the same for the right figure, which is the result for bed topography. We can see that so as more observations are simulated, we have better results, which means that our estimated values are getting closer to the true friction coefficient and then bed topography. So we see some significant improvement near the grounding line, which is shown in red here for both parameters. And at the end of the 30-year estimation period, areas far upstream also show some improvements, but not as much as the near the grounding line. So based on the state and the estimated parameters from data simulation, we run model forward, extending up to like 200 years to investigate the impact of the ensemble data simulation on the model projections. So we use the estimated state and parameters as initial conditions from various points in the data simulations where we saw the last slide. So the B is that the model starts from after the 5 years data simulation, and then C is after 15 years of simulation, and then for D, the model starts after 30 years of data simulations. So this figure shows the changes in ice volume over time for the reference simulations shown in red, and then the forecast simulations without and with the data simulation. So blue is the result with the mean estimate states, and the gray represents each ensemble member. So without DA in figure A, the forecast is blue is tend to underestimate the ice loss over 200 years, and then with a large uncertainty, which is represented by these ensemble simulations. So as more observations are assimilated, the ensemble spread is reduced, and the deterministic this forecast, this blue line gets closer to the reference simulation, which is red lines here. So when we extend our data simulation up to 30 years, the error in the ensemble mean over 200 years decreases, and with the reduced ensemble spread. So now we see that ensemble command filter can recover Phaser conditions and the model state. We try to see the impact of the observations being assimilated. So we set up one more experiment here, which is assimilate both velocity and surface elevation data. And the other one is to assimilate only velocity data into the model. So from these experiments, we can see the impact of assimilating surface elevation data for our model setup. So here we assume a bit more realistic surface elevation, which is the data along this synthetic ground track, which we try to mimic the reference ground track of the ISET2. So here's the result for friction coefficient. So left figure is when we assimilate both velocity and elevation data, and the right figure is when you assimilate only velocity data. So when we assimilate both data, we can get great results, which is similar to previous experiment. And when we assimilate only velocity data on the right, it shows some improvement after 5 years near the grounding line, but after that, it does not show much improvement for both inland and then around the grounding line here. And then when we look at the path of results, the improvement is very similar to what we saw for the friction coefficient. So when you're simulating only velocity data, we see some improvement near grounding line, but after that, we don't see much improvement, still getting this interpolation error between the measurements. So this is the root mean square error for both variables with the simulation time. So blue is for assimilating both observations, and the orange is only velocity simulation. So as you can see here, we see continuing improvement for both variables when we assimilate both observations. And then when we assimilate only velocity, we see some improvement early period of assimilation time, but after that, we don't see much improvement for both variables. So to summarize, we see that ensemble command filter can recover base of conditions and the model states after several assimilation cycle. And then we also see that assimilating both velocity and surface elevation data provides better initial conditions than using only velocity data alone. So although this was for only like idealized model setup, we can apply this method to real glaciers with different observational specifications, like testing the impact of errors and spatial and temporal coverage and so on the model initializations. So I got some future research questions, but I think I'm out of time. So yeah, I'll just stop here. Thanks for listening.
Thanks very much, Youngmin. That was very impressive. So again, if you have questions, please raise your hand and I can call on you to ask a question. Jack Dibb, your hand is raised.
Yeah, that's really interesting. Although I have to say that I'm a little bit confused about sort of a concept in what you did in your experiment. You know, you had a very idealized, as you said, model, you know, of truth. But from Jessica's talk, you know, she was suggesting that the basal friction could change seasonally. And then you're saying, well, we're going to fix it and it should be fixed and it's going to take us 10 years of assimilation to get close to getting it right. But if she's right and it's changing seasonally, and maybe if the whole system is changing a lot because of major mass loss and retreat, wouldn't you expect that bed friction to be changing? If not seasonally, maybe it's even changing tidally. I mean, it could be changing multiple times a day. Who knows, right? But the idea that you needed to assimilate the data for 15 or 20 years to close to come back to what you had as a fixed beds doesn't seem very encouraging to me if the whole system is in a state of huge flux, right? It's nowhere near steady state. And I guess I'm just wondering what I'm missing in your model structure, or why you're so excited that you can, in 10 years, you get closer and closer to something that's fixed that probably isn't really fixed, constant in time.
Okay, yeah, I probably I didn't explain the details of the model, but here the friction itself is not fixed. I have this friction coefficient, and then that's the friction coefficient that I'm trying to estimate. So I assume that friction coefficient itself is fixed for through time. But so yeah, I mean so yeah, I didn't explain the like friction laws here, but we have like friction law that's dependent on velocity and the friction coefficient. I only fix the friction coefficient. So that's the kind of like big assumption here, but we can test like variable friction coefficient like Jessica did in the future. So I'm not sure if that answers your question. But
I'm not sure either, but go ahead to another question.
I could try chiming in a little bit.
Go ahead.
Yeah, so I think like Youngmin, the first half of my talk where I showed more thinking about decadal trends, that was also a fixed basal friction coefficient, just one. It varied spatially like Youngmin's did, but it was one value in time, and that's the most common thing to do for ice sheet modeling. I was interested in seasonal timescale processes, so I expanded kind of our space of the parameters we were calibrating and said, okay, now I have a different friction coefficient each season, and calibrated all of those. And so it's more just what is your the parameter space you're calibrating. And so to do the seasonal calibrations, I expanded that, but mostly in ice sheet modeling, we assume that basal friction coefficient is fixed in time, and use the sliding law to allow basal conditions to vary as velocity and geometry changes.
Thanks.
Thanks. So, so Youngmin, you clearly showed that, you know, in your simulation, you had time series of the observations, the analysis, and the forecast. So you can compute, you know, the O minus A and the O minus F. And sometimes when people do that here for atmospheric data assimilation, they can draw conclusions about the mean biases of the model. Are you able to do that with the O-A and O-F statistics that you generate from your data assimilation? Or are they, particular? Are they functions of particular situations that the O-A and O-Fs occur in?
I'm sorry, I missed the part of your question. Can you repeat that?
So if you compute the observation minus analysis and observation minus forecast,
Yeah.
are you able to draw some conclusions about the biases of the forecast model?
Yeah, actually, I didn't look at the actually like statistics of this experiment, but yeah, I think I know that like other like models, atmospheric models does that with this ensemble data estimation thing. So I think yeah, I'd like to get like more insight from that error estimate. But like Jessica said, I focused on usually the variational approach, and then I just moved to this ensemble data estimation thing, and so I like to get some insight from the other fields as well. Yeah. So
Okay.
yeah.
So you showed that with 30 years of data assimilation, you get much better accuracy than with 5 years of data assimilation. So can you extrapolate to get an idea of how many years are necessary to, for example, provide an accurate forecast, say for 100 years into the future, or on an IPCC or ISMIP timescale?
Yeah, actually, that's a really interesting question. And then that's the one I was trying to answer here with this idea setup. So here with the 30 years, I can get, this 200-year projection almost correct. And then I think 15 years, with 15 years, I can get like almost 100 years. So the reason I chose 30 years is that like I assume that like we have almost 30 years of satellite data we can estimate into our model. So of course, for the real glaciers, we need more tests, but there'll be also interesting questions. So, but I think for this model domain specifically, I think 30 years for like 200 years projection was correct. Yeah.
Okay, great. Hailan?
Yeah, yeah, thank you, Jessica and Yoming. It's not my area, but I enjoyed your presentations. I have a very like general question about the data assimilation. When you simulate the ISG model or snow on the ice, do you consider like the impurities, dust or those ashes deposit on the surface that would affect the albedo of the surface? I know that you consider the snowfall. Maybe, I don't know if you consider rain on top of those, but yeah, I just curious.
So Hailan, I think those would be things that would affect the surface mass balance, which would
So
be
it's
the input
overall
into the ice sheet
considered.
model.
Okay. All right, thank you. Yeah, I just want to confirm. Thanks.
Okay. I should say that I'm leading a NASA project for surface ice sheet data assimilation. So that might be something that we'll look into.
Okay, so for my idealized model setup, I assume that we know we have the like perfect knowledge of other parameters, including the surface mass balance, except for my estimated parameters. And then we usually have like use the surface mass balance from the regional climate model. So we force the model actually not invert for those surface mass balance, but I know that there are other studies that try to kind of correct that surface mass balance using data estimation approach to have like better to get more like correct surface mass balance. So there'll be interesting to have that in the future research. Yeah.
All right, great. It's the top of the hour. If there are no more questions, I don't think there are any more raised hands. Okay. I'd like to thank very much our two speakers, Youngmin and Jessica, for their presentations today. I think this was a great meeting. Wilbert, do we have any announcements? I think we're taking hiatus for February. Is that right? For later February.
I think so. That's 100% sure. I think so.
Okay. That's for our regular February meeting, which is at the end of the month. So this will count as our February meeting. And then the IARPIC team leads will have a discussion meeting this month. And then we'll have announcements for new meetings going forward from there. Hazel, is that it?
That sounds good. Thank you all so
Okay.
much. And yeah, thank you to the presenters. This was really interesting.
Okay. Thanks very much. Bye-bye, everyone.
Thanks for
Thanks.
having me.
Bye-bye.
Thank you. Bye.